So today's class we are going to discuss on distributional semantics, n-gram, word2vec and glove. Imagine that you want to look at the meaning of a word without looking at the dictionary, but looking at the context, looking at the other words that go along with that one, right? So now to understand this one, we need to understand the distributional semantics. And distributional semantics actually talks about words that occur in a context, not just from the dictionary point of view. To understand the distributional semantics, let's start with text representation. So text representation refers to the process of transforming raw text data into the format suitable for analysis into the computational models. So this is important for numerical requirement, that means to understand how this text data is being transformed into a vector or a numerical format, and even finding out the generalization from the data set and some of the features that are required to extract for doing any kind of NLP application, and also the complete semantic understanding. So text representation is the most initial point to get into the distributional semantics. Let's talk about this text representation from some of the techniques. One is from Zipf's law. Zipf's law highlights how a small number of high frequency words dominate the whole corpus, while rare words still carry important meaning. So the second one is bag of word technique. It represents the text as a collection of word frequencies. And TF-IDF is another technique. It highlights the important words by calculating TF, that is nothing but term frequency, and IDF is nothing but inverse document frequency. And word embeddings is a technique which uses the models like word2vec, glove to convert the words into vectors. Let's talk about the Zipf's law. Zipf's law describes the distribution of word frequencies in natural language. So we know that a corpus is nothing but a number of words that are associated with it, right? So we have number of words, and sometimes particular word can repeat multiple times. So now Zipf's law, what it observes is find out the frequency of a word, and now the frequency of the word is inversely proportional to its rank. That means if a word is most frequently being used, let's say it is being used 100 times in a given text of 1000 word limit, and this is the rank 1, right? Now the higher frequency of the word is inversely proportional to the rank. So rank higher means more times the particular word is being repeated. Now the most frequent word appears about twice as often as the second most frequent, and 3 times often as the third one, and so on. So the mathematical formula for Zipf's law is frequency of that particular, or that is nothing but the rank of the word, is inversely proportional to the rank of the frequency table. So now here f of r is the frequency of the word with the rank r. Now let's take an example. Let's take a small text like the cat chased the mouse ran away, the cat caught the mouse. Now we know that there are like list of words, and some words are being repeated multiple times. Now the word frequency helps us in understanding the is nothing but it is occurring 4 times with the rank 1, and mouse occurred 3 times with the rank 2, as you could see here, and cat occurred 2 times with the rank of 3, and chased, run, away, caught all occurred in 1 time with the equal range, and either we can put them in the rank of 4, 5, 6 subsequently. Now the observation is the most frequent word here, that is the, appears 4 times and mouse appeared 3 times. So this shows that the more number it occurs, the less rank it gets, right? So top rank is nothing but it occurs multiple times in the complete corpus. Now bag of words is another technique. So this is a simple technique to convert the words into numerical representation based on the word frequency. So conceptually, let's think about the whole document as bag rather than a sequence. Now let's again take the sentence like the boy packed his school bag in the morning. The boy went to the school. Now, the step 1 in understanding the bag of word technique is, first let's tokenize the data and remove the stop words. The stop words, as we already have discussed, something like the or something like his, in, the, which are like a kind of functional elements. Let's say we don't want it for a particular task requirement, we can just remove them, and we can perform stemming and lemmatization on the top of it. So, the remaining output that we got is, after removing the stop word and performing, let's say here there is no stemming and lemmatization is being done, but we got some kind of words. Now, we have to list all the unique words. If a word occurred multiple times, we are just taking only the unique word out of it. So, that would be the step 2. Now, we have to create a dictionary with mapping of words to a number. So, this shows how be sorted on frequency of occurrences in descending order. So, for example, when you have a vectorization numbers like 0 to 6 and there are words and there are frequencies, we are giving the frequency over here with the number associated to it. So, now we have to create a table in each sentence for the presence of that particular word, either it is there in the bag of word dictionary that we have created it or not. If it is available, we will assign the number 1, else we will assign the number 0. So, now let us take the sentence and we will try to give the numbers like 0 and 1 based on that one, and now the data is being transformed into a kind of list of vectors or numbers that are being assigned, zeros or 1. Now, boy packed school bag morning, now we are getting this representation, and the another one is another representation. So, this representation is one type of vector representation. It helps us to represent, this is in this document, this is the combination of words that are being occurred, whether it is there in the dictionary already or not. Now, it is typically helpful in language modeling and text classification. Of course, it is a very easier and a popular method, but still it do have a shortcoming. So, sparsity of document representation is one of the major shortcoming, and it does not capture the meaning around the word. It just captures the word and its frequency. So, to overcome this shortcoming, the other method that is called TF-IDF can be used. So, what is this TF and IDF? TF is term frequency and IDF is inverse document frequency. So, term frequency is being calculated as how many times, let us say the total number of terms in the document D, from this how many times the term appears in the document, that is a term frequency. Especially we are trying to identify the number of times that word is being repeated in that whole text. So, it represents the local importance of a term. So, also it identifies which word is more prominent given the specific document. On the other hand, inverse document frequency is nothing but it looks at the global importance, looking at number of documents containing the term T. On the top of it, total number of documents. So, it is an inverse logarithm to get the inverse document frequency. So, this idea reflects the global importance of a term that identifies that particular word, either it is a discriminative or an informative across the multiple documents. Now, let us take the same example which we have used for bag of words. Let us say this example like the boy packed his school bag in the morning. The boy walked and went to school. We have created a dictionary already, right? And using this dictionary, now we are going to calculate TF and IDF. The step 1 to calculate the TF is calculate TF of each word for each sentence. So, for example, let us take we have the boy packed his school bag in the morning. After removing the stop words, what we are remaining it is something like this. Now, the total number of words in this particular sentence is 1, 2, 3, 4 and 5 after removing the stop word. And number of time the word boy appears in this sentence is 1. So, now the TF for the boy is 0.2. Now, step 2 is we have to calculate the IDF of each word in the vocabulary. Now, number of sentences containing that word boy including 2 sentences, that's the context window for us right now, and total number of sentences. So now total number of sentences for us is 2, and combining the sentence 1 and sentence 2, now we have the word boy occurred twice. So now let us take that one and create a logarithm, and now IDF is 0. So now multiplying TF and IDF values for each of the word, now we have taken only boy, now we are, let's say, multiplying it for each of the word, now we will get the document vectors, right. So through this TF-IDF model, we can like address some of the shortcomings what bag of word has, especially the context and the meaning. So though it has identified some of the context, it also have some kind of shortcomings. So the shortcoming is the position of the word in the text, whether it occurred in the initial position, whether it occurred after a particular like set of words, or it occurs in the end of the document, that's not been identified through TF-IDF. And meaning of words which have the similar meaning still have different representation, because they are of different graphemic representation. So both of them are written in different way, so definitely they do have a different representation. And relationship is another thing, because relationship between words where they frequently occurring will be missed out. There are some words which always occur together, right. So now TF-IDF might not work better in such kind of context. So that's why we are going towards another text representation method, that is called word embeddings. So word embedding is again a type of word representation that allows words to be represented as dense vectors in a continuous vector space. Now each word is mapped with a unique vector. That's the most important thing here. And similar words are represented as vector that are closer to each other in the whole complete vector space. So that is not being done in TF-IDF. So whereas word embedding can help us in doing that. And word embedding captures some kind of semantic and syntactic relationship between words, because it's all dense vectors. It's able to identify what words coming along with that particular word. The surrounding of the words are being identified. Okay. Now word embeddings are mostly done through a large text corpora using some of the techniques like word2vec, glove or FastText. Okay. So word2vec is nothing but a popular method that learns the word embeddings by predicting the surrounding words in a context window. Okay. Glove on the other hand is a global vectors for word representation. It learns word embeddings by factorizing the co-occurrence matrix of words. FastText, it's an extended form of word2vec, where it represents each word as a bag of character, something like n-gram. So especially it creates a subword information from the word given here and learns the embeddings from these n-grams. Okay. Now let's take this example. Let's say the representation of a particular word, how that representation helps to predict the representation of the other word. Let's take the king is being represented in a vector space here, and the vector space for man is here and women is here. Now using this one, are we able to get the vector space of queen? So queen is nothing but, as we know, king minus man plus women, right. So the position of a king where the masculinity is being removed but women feature is being added, so that result in a queen. So now when we subtract the vector for men from the vector of king and add the vector of woman, so the resulting vector is very close to the vector of queen. So this captures the semantic nuances that particular word carries. So this is the vector math that is being associated with word embeddings. Now these vectors capture semantic relationship between words. Now let's say words with similar meaning are those that appear in similar context. Will they have a vector space closer to each other or not? So this can be indicated through something called semantic similarity. So this is one of the best thing about the word embedding, but still it do have its own shortcomings. As we have seen in bag of word TF-IDF, it can struggle with rare words. Okay, a word occurred only one time. Identifying the vector space using this kind of method is a very difficult one, and it ignores the word order. Word order is not been, again, positional information not captured through this word embedding. So, in such cases, we have to go for contextualized word embeddings. So, that is something called ELMO. This is used for embeddings from language models, and BERT is a language model. Again, it uses bidirectional encoder representation. It's a transformer model. So, this contextual word embeddings helps us in like identifying the word order information very effectively. Having understood what word embedding is, let's get into the distributional semantics. Distributional semantics is a theory of meaning that focuses on the distribution of words in context. So, the idea is that the words that occur in similar contexts tend to have similar meaning, right? If a word occurs in a particular context and it can be substitutable with another word in the same context, definitely it has a similar meaning. And words are represented as vectors in a high dimensional space in the distributional semantics. Words that are similar in meaning again have a similar vectors in this space. So, both are true in the distributional semantic point of view. And this is the foundation for word embeddings such as word2vec and glove, and the later part that is called FastText. Now, the key principles of distributional semantics is contextual similarity. So, words that frequently appear in particular context tend to have a related meaning. That is the underlying principle of distributional semantics. And word vectors are mapped with high dimensional vectors. That means words are mapped as high dimensional vectors, so that we are trying to capture the semantic property associated with the words. And vector operations are a kind of mathematical operations because it captures the linguistic property. So, the linguistic property is something like there is a relationship across the words, and this relationship can be captured through some kind of binary features like let us say a king. King is a plus man plus human plus like in the higher position in the administration, right. So, there are a lot of plus and minus features that are associated with each of the word. Now, these linguistic properties can also be easily seen in the distributional semantic output representation. And the application of this distributional semantics is used for information retrieval, machine translation, summarization and whatnot. These days in large language models, LLMs do use this as the underlying factor to understand how word embeddings are useful, again how context is useful, and how much bigger context with some kind of attention is being utilized. And to evaluate this kind of distributional semantic thing, some of the metrics which include cosine similarity, that's been used in a very popular way, and nearest neighbors in the vector space. And still there are some limitations to the distributional semantics. One is context lost, that is pure distributional models often lose syntactic and positional information. Polysemy is another important thing. So, polysemy is words with multiple meaning. So, let us say the words like bank, as we know, right, bank has multiple meaning. Now, this bank might occur in multiple places. So, this kind of distributional models, especially the simple distributional models like word2vec, they may struggle with polysemy because each word get only one vector, whether it is a bank in the river bank or bank in the financial bank. And size of corpus is another important because it is dependent, the quality of the vector is dependent on the large corpus because that helps us to get the quality word vector. And interpretability, the dimensions of the vectors do not have clear, of course, interpretable meaning. And there may be bias, because the inherent bias that is there in the text can also be captured through the bias in this data, because they are trained on the kind of biased corpus. So, the gender bias and racial bias can also be identified, but the way to mitigate them is we should have some kind of fine tuning method later to mitigate some of this information. Okay, let's talk about some of the models that can be popularly used in distributional semantics. One is n-gram model. So, n-gram is a sequence of n words that occur together in a sentence. So, n-gram models are used to predict, again, the likelihood of a word based on preceding word. That means n words likelihood is predicted through n minus 1 words. Now, let us take into the example. So, 1 gram is nothing but the likelihood of a single word independent of its context. 2 gram is nothing but bigram, the likelihood of a word based on the previous 2 words. And 3 grams are nothing but the likelihood of word based on preceding 2 words. This is called trigram. So, similarly, it can go for any number of gram. So, n-gram model captures the local dependencies, but of course, if you go for a long range dependencies in a sentence, it might struggle. So, now it works based on calculating the probability of the word given the previous n minus 1 word. Now, the probability of sentence is calculated as the product of the probabilities of all the n-grams in the sentence. So, the probability of a word is being calculated separately, and the probability of the complete sentence is again nothing but product of probabilities of each of the n-grams in the sentence. Now, let us take the example, the cat sat on the mat. Now, 2 gram probability for this one is, let us say the probability of sat given the cat, again the probability of on given sat, and the probability of the given on. So, we keep on predicting the probabilities of each word. So, larger n-grams, let us say trigrams, that means 4 grams capture more context, but they require more data to estimate their reliability. So, the strength and weakness of n-gram models are, they are very simple and also intuitive, but works very well with the local dependencies, especially if you want to look at only the adjacent word, n-gram model is the best model. It can be easily implemented in real time application. And the weakness here is it works like limited sparse data will not be enough. It requires a large corpora to estimate the probabilities. And it cannot capture the long term dependencies because information beyond the n word is lost here. And size of the model grows exponentially with n. Now, let us get into the word embedding. Word embeddings are dense vector representation, as we have just seen, are used in a continuous vector space, and they capture both semantic and syntactic relationship. And as we see, similar words will get similar vector representation. So, word embeddings are again learned from large corpus using models like word2vec and GLOVE. So, these embeddings can be used in various NLP tasks such as text classification, sentiment analysis and machine translation. So, word2vec is one of the neural network model because it tries to learn the word embeddings through multiple words. So, it comes in 2 variants. Word2vec can be implemented through continuous bag of words. This is called CBOW. It predicts the word and its surrounding context. And skipgram is another method in word2vec. It predicts the surrounding context given a word. So, they are 2 different things opposite to each other, whereas continuous bag of word predict the word given the surrounding context, whereas skipgram predicts the surrounding context given a word. So, now CBOW is efficient and works well for frequent words, but skipgram works better for rare words because we are predicting the surrounding words of that particular rare word. So, now word2vec learns embeddings by maximizing the probability of co-occurrence between these words and their context. Now, how both the model works, let us understand. So, in CBOW model, the goal is to predict the current word given the surrounding words. So, let us take, given the context, the dash sat on the, right, let us say this is the kind of context. Now, there is a context, there are surrounding words are given. Now, CBOW will predict missing word, that is nothing but, okay, it can be a cat here. So, the model now learns through word embedding, because word embedding already created a dense vector representation, and it maximizing the probability by predicting the correct word given the whole surrounding context. So, training is performed using backpropagation and also some kind of statistical thing. This is called stochastic gradient descent. So, now skipgram on the other hand is the task is to predict the context given a word. Now, let us say given the word cat, now the model should predict the surrounding words like the, sat and on, like the, sat, on. Now, this approach is particularly effective for learning word embeddings from small data sets and for rare words. Now, skipgram actually gives more flexibility to the model and handles long range dependencies better than CBOW. Now, the word2vec, both as we have seen, CBOW and skipgram can also be calculated through this means. So, we have giving the surrounding context, using this it has to predict the word in the CBOW, whereas skipgram given the word like identify the whole context. So, this is how the word embeddings in word2vec works. So, now where do we use this word2vec information? So, especially to identify the semantic similarity, word embeddings can be used to compute the similarity between words. So, king is closer to queen than dog is being actually identified through this word2vec. And document classification, where word embeddings can help us represent the content of documents for tasks like spam detection, topic classification, it will be useful. And in machine translation, word2vec embeddings can improve the quality of machine translation system, where we need to align the similar words across languages. Now, in question answering, embeddings are used to improve the accuracy of answering questions in natural language. And in recommendation systems, in some cases, word embeddings are used to match user preferences with products and content. Okay. Now, let us go into the second word representation technique, that is called GLOVE. So, GLOVE is a global vectors for word representation. It is another method for learning the word embeddings developed by Professor Christopher Manning and his group in Stanford University. And GLOVE is a very popular unsupervised algorithm for word embeddings. So, that is also based on distributional hypothesis. The hypothesis here is words that occur in similar context likely to have similar meaning. Now, unlike word2vec, GLOVE focuses on capturing global word co-occurrence statistics in a corpus. So, it builds a word co-occurrence matrix and learns embeddings by factorizing this matrix. So, it is effectively useful for rare word meanings and also long range dependencies that is not being done in the word2vec context. So, the model captures both local and global context in the embedding. So, in the context of word2vec, as you see in the picture, so you could see there is a kind of word vector representation that predicts us what would be the word of each of the representation. So in the glove representation, as you could see, man and woman are also being identified. Even the long-term dependencies are also being identified. Let's say company and its CEO can also be identified. City and zip code and comparative and superlative degrees of adjectives can also be identified. Similarly, all other relations are identified. So now the relation, it can be a horizontal or a vertical, or it can be any diagonal shapes that will predict us. That means the word representation, vector representation, can help us in understanding how these words have a similar context. Now, how is it been done? It's been done through co-occurrence matrix. Let's take the following co-occurrence matrix for these 3 sentences. I like deep learning, I like NLP, I enjoy flying. Now in this case, looking at these 3 sentences, let's create the co-occurrence matrix. That means the count of each word and their co-occurrence. Let's say I and I occurred 0 times, but like and I occurred 2 times in the text, right? Similarly, enjoy and like occurred enjoy and like occurred 0 times, whereas I and enjoy occurred 1 time. Similarly, we are trying to understand the co-occurrence matrix of each word with another word in the complete corpus. So this matrix demonstrates how words co-occur within a window size of 1. Now glove starts by constructing this co-occurrence matrix, where each cell represents the number of times a word appears near another word in a large corpus. So it then factorizes this matrix to reduce its dimensionality. So it results in the word embedding. So the key insight is that ratios of word co-occurrences are more informative than absolute counts. So now glove captures both syntactic and semantic word relationship by balancing both local and global information, because co-occurrence is one important thing which helps us to know whether I is followed by like, then there is a kind of syntactic element associated with it. Now the strengths of glove is, in the context of global, it captures both global as well as local relationship, and of course very robust than purely the local models like word2vec. It used efficient training because it can be trained faster than word2vec, especially for the large corpora. And it handles the rare words because glove embeddings can better handle rare words since the model leverages the co-occurrence statistics. And rich semantic information is captured through the glove because it captures semantic nuances that are useful for downstream tasks like machine translation, sentiment analysis, and etc. And interpretable dimensions, because some of the dimensions in the glove embeddings have interpretable meaning, such as capturing analogies like king minus man is nothing but female part, and plus women, if you add, it is nothing but queen, right? So understanding these analogies can also be done by glove. Now the difference between glove and word2vec, as we just have discussed, word2vec learns word embeddings based on local context, that means the sliding window, and it uses the 2 main architecture. One is CBOW, another one is skipgram, and it captures the local dependencies between words. Glove, on the other hand, learns the embeddings from global word co-occurrence information. It builds the co-occurrence matrix and factorizes it to learn their embeddings. And it captures both local and global word relationships. And the difference between glove is it overperforms, definitely outperforms when you compare it with word2vec, especially for the task where the long dependencies are needed to be identified. And word2vec, of course, it's a best suitable model for handling frequencies and short range dependencies. So the third method, that is a vector representation method under word embeddings, is FastText. FastText is a word embedding model. It improves the word2vec by considering subword information. So, subword information is nothing but splitting that word into multiple smaller parts and identifying their frequencies, which allows of course handle the rare words and also out of vocabulary that is not ever seen in the corpus when it's been trained on. So, instead of representing each word as an atomic entity, FastText represents words as a bag of characters, that is nothing but n-grams. So, this model is particularly useful for languages, morphologically rich languages where words can have different forms. And it provides both supervised and unsupervised learning approaches for text classification. So, how FastText works? Let us start with subword information. FastText splits words into n-grams. They are nothing but subword units. For example, the word where might be split into 3 grams, something like WH, WHE and her, ERE or RE, right. So, it can be split into any way. Now, each word is represented as the sum of its character, that is n-grams, so that it allows the model to capture the internal word structure. And this also allows the FastText to generate vectors for unseen words based on their subword composition, which is an advantage over the word2vec. And it still uses CBOW or it can also use skipgram models in the context similar to word2vec. So, the advantage of FastText is better for rare words. Since we are breaking the word into subwords, it performs better or rare words or misspellings. And it handles out of vocabulary words because FastText can generate embeddings for words it has never seen during the training period by combining these embeddings into subwords. And it also works with morphologically rich languages because FastText is more effective for languages with complex and word structure, something like Finnish, Turkish, Tamil, Telugu kind of languages. Of course, Hindi is not that morphologically very rich though. And it's efficient and scalable because it's fast to train and can handle the large scale data set efficiently. And it's used in a more better way for text classification because in addition to word embeddings, it can also be used with some kind of supervised technique with a state-of-art performance. And now the use cases of the word embeddings that we have seen like word2vec or GLOVE or FastText are always useful for any of the NLP application because starting with sentiment analysis, we need to get the sentiments expressed in the text. So, we have to build the sentiment classifier where this can be used. And named entity recognition is another type where embeddings help to recognize and classify the proper names in the text as we have already seen. And in machine translation also it has been used in especially modern machine translation systems of course to map across the languages. And speech recognition, of course, it improves the speech to text accuracy by capturing the word context. And in chatbots, it's used to understand the user queries and provide relevant information, right. In all cases, embeddings are being used. Now, evaluating the word embeddings are another important thing. Word embeddings are evaluated through different means because we are evaluating their ability to capture word similarities and their analogies. So, intrinsic evaluation and extrinsic evaluation can be done. It evaluates intrinsic evaluation, evaluates the embedding using predefined word similarity and their analogy data sets. And extrinsic evaluation is mostly how it's performing in the downstream task, something like sentiment analysis or machine translation kind of task. And metrics which are being more commonly used are cosine similarity, analogy completion and word pair similarity scores. So, now the distributional semantics forms the foundation of most of our modern word embedding technique because we are capturing the meaning of the word based on the context. So, now word embeddings like word2vec, GLOVE definitely provide efficient and powerful representation for words in NLP task. While n-gram models are of course simple and effective, but they have a short range dependencies. They cannot go beyond a particular range, whereas the other embeddings can help us getting the embedding so that the complex semantic relationships are captured. So, and again evaluating these embeddings are also very important, because how well these models works in a real time application are important.